So here goes the roadmap for this chapter. At first we would look at some basic ideas in differential equations, like what is an ordinary differential equation, how does it differ from a partial differential equation, what is meant by order, what is degree, what is a linear differential equation, what is a nonlinear differential equation, what is a linear homogeneous equation, and what is a linear non-homogeneous equations. Next, we would learn what is the concept of a solution by taking a first order ODE as an example. Then we will learn in detail about the different methods to solve first order ordinary differential equations. Then we will have a look at second order constant coefficient ordinary differential equations. Essentially, we'll look at homogeneous equations first. We'll also have a look at second order variable coefficient differential equations. And mainly we'll focus on the solution of the Euler-Cauchy equation. After these, once the homogeneous equations are done, we will look at non-homogeneous equations. So essentially we'll study constant coefficient non-homogeneous equations, and we are interested in finding the particular integral of these equations. We'll learn the method of undetermined coefficients because this gives an insight. We'll also learn the shortcut method, which you can use in the exam to arrive at a quick answer. You could also use the method of variation of parameters, which is a little bit long but has its own advantages in certain problems. After this, the solutions of ODE is done. We'll go to PDEs. First, I'll introduce you to a few PDEs, the important PDEs that you learn. Then we'll also learn briefly the classification of second order PDEs based on their nature. That is, we'll classify them into parabolic, hyperbolic, and elliptic PDEs. Finally, we'll also see how to solve these PDEs using the method of separation of variables. This is a method which works only for linear PDEs. Essentially, we are going to study how to solve the Laplace equation, heat equation, and wave equation using the method of separation of variables. So this is a roadmap for this chapter on differential equations. Okay, let's start with the basic ideas of differential equations. The first idea is, what is an ordinary differential equation and how does it differ from a partial differential equation? A differential equation having only one independent variable is called an ODE, whereas if a differential equation contains more than one independent variables, then such a differential equation is called a PDE. Now, how to identify the dependent variables and independent variables? Usually, okay, the variables that appear in the denominator of the derivatives are independent, and the variables that are in the numerator of the derivatives, those are dependent variables. This is just a small identification, but not the basic definition of dependent and independent variables. So just quickly to identify what are the dependent and the independent variables. Okay. Second idea is the order of the equation. The order of the differential equation is the order of the highest derivative appearing in the equation. So you look at the highest derivative in the equation, whatever is the order of that derivative, that is the same as the order of the differential equation. Now coming to the degree of a differential equation, the degree of a differential equation is the degree of the highest derivative appearing in the equation. So first you remove the fractions and radicals from the derivatives, that is, the derivative should not appear in the denominator and the derivatives should be free of radicals. So you remove that in the equation and then you look at the highest derivative. Whatever is the degree of the highest derivative, that is the degree of the differential equation. Next is this important idea of linear versus nonlinear equations. Again, this is not the basic definition of linear equations, but just how to quickly identify what is meant by linear equation. I'll come to the definition once I have finished this idea. After identifying the independent variables and the dependent variables, you should check these three things. That is, the dependent variable and all its derivatives should have a degree of 1. That is, if y is the dependent variable, then y, dy by dx, d square y by dx square, they should all have a degree of 1. Second condition, the dependent variable and all its derivatives do not appear in composites of other function. For example, you cannot have sine y. If y is the dependent variable, you cannot have sine y in the equation. Y has to appear as y. and dy by dx should appear as dy by dx. They should not appear in terms of composites of other functions. The third condition is the coefficients of the dependent variable and all its derivatives should not contain the dependent variable. So the coefficients can contain the independent variables, but the coefficients should not contain the dependent variables. If these 3 points are satisfied, then your equation is a linear equation. So as I told you, this is not the basic definition of linear equations. Rather, this is a quick way to check whether your given equation is linear or non-linear. These kind of questions will be asked in the exam. So quickly, how to answer it in the exam, this will help you. Rather, the actual definition will be very difficult to apply. So I'll not tell this actual definition now. Actually, the basic definition of linear equations has to do with homogeneity and superposition. That is, a linear equation will obey both homogeneity as well as superposition. I'll come to it when I explain about linear second order equations. Till then, I'll not talk about the basic definition of linear equations. This is sufficient for identifying whether your given ODE or PDE is linear or non-linear. The conditions are all on the dependent variables and there are no condition on the independent variables. Homogeneous versus non-homogeneous equations. This classification is relevant only for linear equations. If a differential equation is non-linear, we'll not worry about whether it's homogeneous or non-homogeneous. This is specifically classification is done for linear equations. So linear differential equations can be classified as being homogeneous or non-homogeneous if all the terms in a linear differential equations have the dependent variable, then the equation is said to be homogeneous. Every term in the equation should have the presence of the dependent variable. Then you say it is homogeneous. In a linear non-homogeneous equation, however, there is at least one term which does not contain the dependent variable. So it is either made up fully of independent variables or it could be a constant term also. But the term does not have dependent variable. Such terms are called non-homogeneous terms, and if an equation has these terms, then the equation is said to be non-homogeneous. Now what is the physical meaning of these terms? The non-homogeneous terms physically represents either a force or a source. So these are usually called the source terms in a PDE, but in an ODE they are usually they represent some kind of a force. Now let's take a few examples to quickly apply these ideas and maybe we'll answer certain questions. In the first example here, you're given an equation. This is a differential equation. A differential equation is an equation that contains derivatives. So first of all, is this an ODE or a PDE? That's the first question. This is clearly an ODE. Why is this an ODE? This is an ODE because there is only one independent variable. The dependent variable is y and the independent variable is x. So y will be the dependent variable and x is the independent variable. Now the next question we can ask is, what is the order? The order is 2. The highest derivative in the equation is 2. So this equation has an order of 2. What is the degree of this equation? The degree of this equation is 1 because the highest derivative is this and this has a degree of 1. So the degree of this equation is 1. Is this linear or non-linear? This is clearly a non-linear equation because there are two terms which make it non-linear. First, there is y square. The dependent variable is y. So the y square term, y has a degree 2. This is definitely a non-linear term. And you see that dy by dx term has a coefficient which is the dependent variable. So again, this term is also a non-linear term. So there are two non-linear terms, this and that. This is a linear term, that's a linear term, but because of these two non-linear terms, this equation is non-linear. And if it is non-linear, we won't worry about classifying it into homogeneous or non-homogeneous. Now let's come to the second example. This is a partial differential equation because u is the dependent variable and this depends on x as well as t. X and t are the independent variables, u is the dependent variable, and hence it is a PDE because it contains two independent variables. Now, is this linear or non-linear? It is clearly a linear PDE because all the derivatives of the dependent variables, they are having a degree 1 they have a constant that does not contain u, which is the dependent variable, and the dependent variable does not appear in terms of composites. So this is clearly a linear equation. And is this homogeneous or non-homogeneous? This is homogeneous linear equation because there are only two terms, both the terms contain u. So this is linear as well as homogeneous. And what is the order? The order is 1, it's a first order PDE, and the degree is also 1. Now, third example, this is a small variation of this above equation. This is called the inviscid Burgers equation, whereas this is called the linear convection equation. Again, this is a PDE, u is the dependent variable, x and t are independent. However, this PDE is non-linear because of this term. The derivative of the dependent variable has a coefficient which contains the dependent variable. Now coming to the fourth example, this is the famous Laplace equation, and this equation is linear. You can check all the three conditions are satisfied. Again, the dependent variable is u and the independent variables here are x and y. It is a second order PDE which has a degree 1. The last example, this is an example for a Euler-Cauchy equation. So this is an ODE because there is only one independent variable and one dependent variable. Y is the dependent variable and x is the independent variable. And what is the order? The order is 2, second order, degree is 1, and this is clearly linear because the dependent variable y appears, has a degree 1, all the derivatives also have a degree 1. They appear as themselves, they don't appear in terms of other functions, they are not composites. Thirdly, if you see the coefficients, this dependent variable term has a coefficient 4. First derivative term has a coefficient x. Second derivative term has a coefficient x square. They do not contain y. So this is clearly a linear equation. Since it is linear, you can also say whether it is homogeneous or non-homogeneous. This is clearly non-homogeneous because of the presence of this term. All these three terms contain y, but this term is free of y. So this term is the non-homogeneous term. I hope this clarifies the definitions I had given so far for order, degree, linear, homogeneous, and so on. We'll move to the second topic, which is solution of first order ordinary differential equations. If you write a general form for a first order ODE, it should be a function of x, which is the independent variable, y, which is the dependent variable, and now the derivatives of the dependent variable. Because it's a first order ODE, only one derivative, the highest derivative is the first derivative, so it stops there. So an equation which contains x, y and dy by dx, a function of that, this is a first order differential equation. So that's the general form of a first order equation. Now we'll first understand what is a general solution and what is the meaning of integral curves. A graph of a solution of the first order differential equation f of x, y, y dash equal to 0 is called an integral curve of the equation. So if you find a solution to this equation and you draw the graph of it, the graph is called the integral curve of that equation. We'll take an example pretty soon. If we know the general solution, we obtain an infinite family of integral curves, one for each choice of the arbitrary constant. So in fact, the general solution is made of not one curve, but it's made of a family of curves. And for each choice of the arbitrary constant, you get one integral curve. So let's take an example to understand what is the graphical picture of general solution to an first order ODE. The example we'll take is this dy by dx is equal to minus x by y. Minus x by y. Now we'll solve this differential equation using the method of separation of variables. That method is quite simple and I hope you are familiar with this. So you separate the variables, you get y dy equals minus x dx. You move the y here and you move the dx there. So all the y variables are on the left side, all the x variables are on the RHS. Now after the variables are separated, you can integrate both sides. So integral y dy is equal to minus integral x dx. Now this is a very simple enough integration. Y square by 2 is equal to minus x square by 2 plus an arbitrary constant which I'll call it as c dash. Now you rearrange, you get x square plus y square equals twice c dash. Okay, so you can take the negative x square term to this side, you get x square plus y square whole divided by 2 equal to c dash. I can also move the 2 here. Now together I'll call this 2c dash as the constant c square, and I get x square plus y square equal to c square. This is the general solution to this ODE. This is the first order ODE. The general solution to that is this. Now, what is this equation? You're already familiar with this equation. This is the equation of a circle. And for any arbitrary constant, this equation is a solution. So this is not one circle, but this is a family of circles. Let me explain the idea. Now, if you fix one constant, then you will get one circle of radius c. But since for any constant c, this equation will satisfy the ODE, so it is a solution for the ODE for any arbitrary constant. You get a family of concentric circles of different radii, all these being solutions to this differential equation. So now what is an integral curve? Any of this circle will be an integral curve to this ODE, and all these concentric circles which are centered at the origin having different radii, they are all solutions to this ODE, and they form the family of curves, family of integral curves. So this is the idea of a general solution to an ordinary differential equation. Now we will learn what is meant by a first order initial value problem, or in short IVP. Now let's start with the example first. Now what is meant by an initial value problem? An ODE plus an initial condition together is called an initial value problem. Now we'll consider the same ODE but with this initial condition, that is y of 0 is equal to 2. You have to read this as when x is equal to 0, y takes a value 2. Now the solution to the ODE is the same. We get the solution as x square plus y square is equal to c square. This is the general solution where c is any arbitrary constant. If this is any arbitrary constant, this equation will obey only the ODE. Now for this equation to also obey the initial condition, we can substitute the initial condition, that is when x is equal to 0, y should be equal to 2. That's what the initial condition says. So you substitute in the general solution 0 square plus 2 square equal to c square, or you get the answer c square equal to 2 square or 4, and hence you get the solution now as x square plus y square equal to 2 square. This should be the solution. Now this solution satisfies both the ODE as well as the initial condition. But for any arbitrary constant c, this equation will only satisfy the ODE, it will not satisfy the initial condition. So now this is the solution of the initial value problem. Now if you look at this equation, it is no longer a family of curves, but it is only one curve. And if you look at that one curve, this curve will pass through the initial point. What is the initial point? The point given by this initial condition, that is x is equal to 0, y is equal to 2, or the point 0, 2. Say, let me call this point to be the point 0, 2. So that's the initial point. Now from among the family of curves, the curve that passes through the initial point, that's going to be the solution to the initial value problem. Now we'll read this theory part. The general solution of a first order ODE contains an arbitrary constant, hence there is an infinite family of curves. Just this ODE has this general solution. Because of the arbitrary constant, it's a family of curves. If we specify the solution is to pass through a particular point, now you say this condition is there. This is an initial condition, the curve passes through this point. Then we must find the particular integral curve passing through this point. This is called an initial value problem. So for the first order initial value problem, which is made of a first order ODE plus an initial condition, x0, y0 are numbers. This particular solution is one curve among the family of curves which passes through the initial point. The general form of the solution, that is the integral curves of a first order equation. Now let's learn the various solution techniques. That is, given a first order equation, how do you solve that equation and obtain the general solution? So these are the solution techniques that are commonly used for solving first order ordinary differential equations. The first method is called the variable separable method. How do you identify, that is, what is the general form of this variable separable method? There will be a function of y dy equating a function of x dx. Your original equation may not be of this form, but you'll be able to rearrange and get all the variable y variable on one side and all the x variable terms on the other side. If this happens, then you say that the equation is of the variable separable type. Now once you have separated the variables on the left and the right sides, to obtain the solution, you just have to integrate both sides. If you integrate both sides, you will get the solution to the variable separable type equation. So this is the easiest type of equation in first order, and many equations are of variable separable type. The second category is the homogeneous equations. The general form of the homogeneous equations is of two types. You either have dy by dx equal to a function of just y by x. Y and x do appear, both appears, but they appear only as a ratio y by x. They do not appear separately, but you can show that they appear only as a ratio y by x. Or sometimes you see the form dy by dx is a function of xy divided by another function g of xy, where f and g are both homogeneous functions of the same degree in x and y. You know what is meant by a homogeneous function? If you replace x and y by tx and ty, then you should get t power n into f of x comma y. Then n is the degree of this function. So I request you to refer to what are homogeneous functions and what is the degree of a homogeneous function in functions. So if both of these are homogeneous functions of the same degree, then you say this equation, this ODE, is of the homogeneous type. If it is of the homogeneous type, then how do you solve it? You use the substitution y is equal to vx, or the ratio y by x equal to v. Both are one and the same. Now you take a derivative of this equation, you get dy by dx equal to v plus x into dv by dx. So wherever you have y, you put the substitution v into x. And wherever you have dy by dx, you use this substitution for that in this equation. So you get rid of dy by dx, you get rid of y, you only have v and x. Now if you rearrange, you will see that the equation would have become a variable separable in v and x. And once it's variable separable, you know how to solve, you just integrate and obtain the solution. So that is about a homogeneous equation. Now coming to the linear equation, this is the general form of a linear equation, and for that matter, this is the only form in which a first order equation can be linear. Remember the conditions? The dependent variable and the derivative should have a degree of 1. The dependent variable and derivative should not appear in composites of other function. Dependent variable and derivative coefficients should not contain the dependent variable. So if you put all the conditions, you can show that this is the most general form of a first order linear equation. Suppose you have another function of x here before the derivative, you can of course divide it and then you can write it always in this form. So this is the general form of a first order equation, a first order linear equation. That is, if a first order equation has to be linear, it definitely has to be of this form. Now for a linear equation, you first find something called the integrating factor, which is e to the power of integral p dx. After finding the integrating factor, you can directly substitute in the solution, which is given by y into e power integral p dx equals integral q e power integral p dx dx plus c. You have to memorize this solution. Of course, we have learned how to obtain the solution, but now you have to memorize this solution. Finally, exact equations are of the form m dx plus n dy equals 0, along with the condition dou m by dou y equal to dou n by dou x. Just m dx plus n dy equal to 0 is never exact, but this along with this condition is an exact equation. Once you know it is an exact equation, you can directly obtain its solution using this shortcut method, that is integral m dx treating y as a constant plus in the second integral you take only the terms of n does not containing x, and that you integrate with respect to y and equate it to constant. So the expression you get will be a solution to this exact equation. So these are the various solution types for first order ordinary differential equation. We will also take a special case of an exact equation and an inexact equation which can be made into an exact equation. So we'll look at integrating factors for exact equation now. Sometimes a differential equation of the form p dx plus q dy equals 0 may not be exact. That is, dou p by dou y need not be equal to dou q by dou x. So this is an inexact equation. But if you multiply this equation both sides by mu, which is some function, an inexact equation has now become an exact equation because dou by dou y of mu p is equal to dou by dou x of mu q. So this unknown function or this function mu of x comma y, when you multiply this function to an inexact equation, it became an exact equation. Such a function is called an integrating factor to an inexact equation. Okay. So what is meant by integrating factor? If the differential equation p dx plus q dy equal to 0 is not exact, that is dou p by dou y is not equal to dou q by dou x, we may possibly make it exact by multiplying it with a suitable function mu of x comma y, which is called an integrating factor. I don't say such a mu is always a guarantee, but some inexact equations can be made exact by multiplying with an integrating factor. So this equation mu p dx plus mu q dy equal to 0 becomes exact with this condition satisfied. Dou by dou y of mu p is equal to dou by dou x of mu q. Okay, that is it about solution of first order equations. Next we'll be moving on to the solution of linear second order homogeneous equations.